Now I'd like to talk about my all-time favorite numbers. These are the Fibonacci numbers. Fibonacci numbers are very easy to understand. They start with the numbers 1 and 1. In fact, they're as easy to understand as 1 plus 1, which is 2. Next, you add 1 plus 2 together to get 3. Then 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13, 8 plus 13 is 21, and so on. 34, 55, 89, 144. Look at those numbers. Get comfortable with those numbers. We're going to see a lot of those numbers in this lecture. So, first of all, who was Fibonacci? Fibonacci was probably the most important mathematician of the 12th century. He wrote a book called Liber Abaci, which was the book of calculation, which was the very first book to teach arithmetic to the Western world. I mean, back then they were using Roman numerals and other clunky devices. Fibonacci was the son of a merchant, and he traveled all around Europe and Africa and encountered the Hindu-Arabic system of doing arithmetic and saw that it was so much superior to what was currently in place that he wrote a textbook that would teach people how to do these mathematical exercises with this new number system. So, and one of the problems from this book had to do with rabbits. Okay, and imagine the following scenario. You've got rabbits who never die. Okay, it's not a very realistic situation, but you have these rabbits that never die. They mate every month, and they produce a male and a female pair. After 1 month, the rabbits are mature and begin mating. So let me give you a picture of that. So you start off with one pair of rabbits. Okay, see, I've got one pair of rabbits there. And right now they're little baby rabbits, so they don't produce any babies. The next month, they are mature rabbits. They're adults. Okay, it doesn't take long for a rabbit to become an adult, I guess. The following month, those adult rabbits have a pair of baby rabbits. And now we have 2 pairs of rabbits. The next month, we'll have 3 pairs in our system. Why do we have 3? Because all the rabbits that were alive are still alive, and the adult rabbits have produced children. So we now have 2 pairs of adults and 1 child pair. So that's 3 pairs of rabbits. What do we have the next month? Well, all the rabbits that were alive in the 4th month, all 3 pairs of rabbits, they are still alive. And the 2 adult pairs have produced baby pairs. So we have 5 pairs of rabbits. Now, how many pairs of rabbits will we have in the next month? Well, figure it out. We have all 5 of the rabbits that were pairs of rabbits that were alive then in month 5, plus all the rabbits that were alive in month 4 are going to have babies now. And that's why the number of rabbits we'll see in the next month is 5 plus 3, which is 8. So the question was, how many rabbits are we going to see after 12 months? And by continuing this process, you'll see we have 1 pair, 2 pair, 3, 5, 8, 13, 21, 34, 55, 89, 144 pairs of rabbits in the 12th month. Okay, let's take a look at these Fibonacci numbers from a more mathematical standpoint. Here's how they are defined. We start off, again, it all begins with 1 plus 1. We define F1 to be the first Fibonacci number, F2 equals 1 to be the second Fibonacci number, and then we have what's called a recursive equation that says the nth Fibonacci number is equal to the n minus first Fibonacci number plus the n minus second Fibonacci number. So let me ask you a question. What would you get if you added up all the Fibonacci numbers? Well, infinity, right? Because they go on forever. Okay, let me ask a better question then. What would happen if you were to add up all the Fibonacci numbers together and then stop at some point? So for instance, we see 1 plus 1 is 2, and 1 plus 1 plus 2 is 4, and 1 plus 1 plus 2 plus 3 is 7, 1 plus 1 plus 2 plus 3 plus 5 is 12, and so on. 1 plus 1 plus 2 plus 3 plus 5 plus 8 is 20. Do you see a pattern with those numbers? 1, 2, 4, 7, 12, 20? May not be obvious yet, but what if I wrote those numbers as 2 minus 1, 3 minus 1, 5 minus 1, 8 minus 1, 13 minus 1, 21 minus 1, 2, 3, 5, 8. Who do we appreciate? Fibonacci, of course, right? Those are the Fibonacci numbers in disguise. They were off by 1 just to confuse you. Now, why does this work? Well, I'll give you 2 explanations for why this works. One of them is it works in the beginning and it will keep on working. How do I know it will keep on working? Well, if you see that 1 plus 1 plus 2, 3, 5, 8 adds up to 21 minus 1, what's going to happen when you add the next Fibonacci number to that system? What's going to happen when you add 13 to that system? Well, then the 21 plus the 13 are going to join forces in a Fibonacci way and get the next Fibonacci number, 34. So 21 minus 1 plus 13 is going to be 34 minus 1, and that pattern will continue forever. This was actually our first example of what's called a proof by induction, and we'll see more of those in a subsequent lecture. Here's another argument that I think is a little bit more direct. You might like this one better yourself. All right, I'm going to show you another reason why 1 plus 1 plus 2 plus 3 plus 5 plus 8 is 21 minus 1. You see that first 1? Let's replace that with 2 minus 1. And that second 1, let's replace that with 3 minus 2. And that subsequent 2, we'll replace that with 5 minus 3, and then 8 minus 5, and 13 minus 8, and 21 minus 13. Okay, so I'm representing each of those numbers as the difference of 2 Fibonacci numbers. And now look what happens as I add those numbers together. So I have 2 minus 1 plus 3 minus 2. The 2's cancel. I have a positive 2 and a negative 2, and those cancel out. And then when I add the 5 minus 3, the 3's cancel. And then the 8 minus 5, the 5's cancel. And the 13 minus 8, the 8's cancel. And the 21 minus 13, the 13's cancel. We have massive cancellation, annihilation here. This is what mathematicians call a telescoping sum. And when the dust settles, what's left of this sum? All that's left is that 21 on the right that hasn't been canceled yet, and that little minus 1 at the beginning that never got canceled. And so when you add all those numbers together, you're going to get 21 minus 1. We can write this in a nice formal equation that says, actually what mathematicians call an identity, that f1 plus f2 all the way up to fn, all the way up to the nth Fibonacci number, is fn plus 2 minus 1. That is, the sum of the first n Fibonacci numbers is equal to the n plus second Fibonacci number minus 1. All right, here's another question. What would happen if you were to sum the first n even positioned Fibonacci numbers? That is, what's f2 plus f4 plus f6 all the way up to f2n? Well, the first thing we should do is look at the data. So f2 is 1, f4 is 3, f6 is 8. As we add these numbers up, we have 1 plus 3 is 4, 1 plus 3 plus 8 is 12, 1 plus 3 plus 8 plus 21 is 33. Do you see the pattern? The Fibonacci numbers haven't disguised themselves enough for you yet, right? Because this time you see it. We have 2 minus 1, 5 minus 1, 13 minus 1, 34 minus 1, 2, 5, 13, 34. Those are Fibonacci numbers, okay? But they're every other Fibonacci number. We have f3 minus 1, f5 minus 1, f7 minus 1, and f9 minus 1. So let's see why that works. Okay, I mean, this is a beautiful pattern, but why does it work? Well, let's look at the last equation. 1 plus 3 plus 8 plus 21. We'll leave the 1 alone, but the 3 will replace that as 1 plus 2. And the 8, we'll write that as 3 plus 5. And the 21, we'll write that as 8 plus 13. So as I'm adding every other Fibonacci number, what I really have are 1 plus 1 plus 2 plus 3 plus 5 plus 8 plus 13, which is exactly the same pattern that we had before. And so that's 34 minus 1, just like we saw before. Okay, here's another one. What if I were to add the sum of the odd positioned Fibonacci numbers? That is, what's f1 plus f3 plus f5 all the way up to f2n minus 1? This pattern's even easier to see. No disguise this time. Right? We start with 1, and then 1 plus 2, and then 1 plus 2 plus 5, 1 plus 2 plus 5 plus 13. We see the numbers 1, 3, 8, and 21. Well, those are just Fibonacci numbers, no disguise this time. And why does that work? Well, we'll leave the 1 alone and do the same thing we did before. We have 2 is 1 plus 1, 5 is 2 plus 3, 13 is 5 plus 8. Add all those together. We have the same Fibonacci sum, except we have an extra 1 at the beginning. And that extra 1 will cancel that minus 1, leaving us with a final answer of 21. In general, we have that f1 plus f3 plus f5 up to f2n minus 1 is equal to f sub 2n exactly. All right, here's a different pattern for you to contemplate. Which Fibonacci numbers are even? Well, let's look at the data, see what it says. So let's see, the f3 is even, f6 is even, f9 is even, f12 is even. This seems even easier a pattern to see, right? Namely, every third Fibonacci number appears to be even, right? We have odd, odd, even, odd, odd, even. Why will this pattern continue? Will this pattern persist? Well, forget about what the Fibonacci numbers are. Just look at the fact that they start off odd, odd, even. Now, what happens when you add an odd number to an even number? You're going to get an odd number. And then when you take this even number plus this odd number, you're going to get another odd number. And when you add this odd number to this odd number, you're going to get an even number. Oh, and now we're back to where we started. Odd, odd, even. Okay, so that proves that every third Fibonacci number will be even. And what's more, anything that isn't a third Fibonacci number won't be even. It will be odd. Now, if you like that pattern, it gets even better. What if we look at every fourth Fibonacci number? What do we have here? We have 3, 21, 144. Believe it or not, every fourth Fibonacci number is a multiple of 3. Moreover, the only multiples of 3 among the Fibonacci numbers occur as every fourth Fibonacci number. So for instance, F40 is guaranteed to be a multiple of 3, and F41, F42, and F43 are guaranteed not to be multiples of 3. It gets even better. Every fifth Fibonacci number is a multiple of 5. Every sixth Fibonacci number is a multiple of 8. And the only multiples of 8 are F6, F12, F18, F24. I mean, how's this for a beautiful theorem? The number Fm divides Fn if and only if m divides n. But it gets even better. Let me ask you this question. Forget about Fibonacci numbers for 1 second, but just 1 second. What is the largest number that divides 70 and 90? And in other words, what is the greatest common divisor of 70 and 90? I hear you say 10, exactly. 10 is the largest number dividing 70 and 90. Well, get this. What is the largest number that divides F70 and F90? What's the largest number that divides the 70th Fibonacci number and the 90th Fibonacci number? Believe it or not, it's the 10th Fibonacci number. And in general, the greatest common divisor of Fm and Fn is always a Fibonacci number. And it's not just any Fibonacci number, it's the most poetic Fibonacci number you could ask for. That is to say, the greatest common divisor of Fm and Fn is f of the greatest common divisor of m and n. And that is, the GCD of the f's is f of the GCDs. It just doesn't get prettier than that. But I'll try. Here's another question. We were talking about prime numbers in a previous lecture. Which Fibonacci numbers are prime? Well, if you look on our list, we have a 2, a 3, a 5, a 13, an 89. It turns out the prime Fibonacci numbers are F3, 4, 5, 7, 11, 13, 17. There's a pattern there. Except for that F4, which we'll ignore, it looks like we're seeing prime indices, right? That is, and in fact, if your index is composite, except for 4, which is sort of a special case because it's 2 times 2, and F2 and F1 are both 1. But except for the case of F4, if you are F of anything composite, you're guaranteed to be composite. That's actually a consequence of that M divides N if and only if Fm divides Fn theorem. But what would be more interesting is it the case that every prime index produces a prime Fibonacci number? Well, as is often the case with prime numbers, it's hard to pin things down. And here, if we were to go just a little farther out in the sequence, F19, 19 is prime, and F19 is 4,181, which might look prime to you, but in fact, it's 113 times 37. So F19 is not prime. However, the only places we see primes along the Fibonacci trails is in the 4th position and in the prime positions. In fact, an unsolved problem in mathematics is, are there infinitely many prime Fibonacci numbers? Nobody knows the answer to that question. If you could solve that problem, you would achieve immortality. And very few places in life that you can achieve immortality, right? I mean, but proving a mathematical theorem and being the first person to prove a mathematical theorem guarantees that people are going to know what you've accomplished for centuries. We still know some of the brilliant proofs that were created by the ancient Greeks. Anyway, here's another interesting result. Every prime, even though we don't know if there are an infinite number of prime Fibonacci numbers, we do know this. Every prime divides a Fibonacci number. In fact, if P ends in 1 or 9, then P divides Fp minus 1. And if P ends in 3 or 7, then P divides Fp plus 1. So for instance, 7 divides F8, 21. And 11, which ends in 1, is going to divide F10, which is 55. 13, which ends in 3, is going to divide F14, which is 377, which happens to be 13 times 29. All right, we know that if we add consecutive Fibonacci numbers together, we get the next Fibonacci number. That's how they are born. Let's look at the squares of Fibonacci numbers. I like to square numbers, you know. Let's see what we have. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 5 squared is 25, 8 squared is 64, 13 squared is 169, 21 squared is 441, and so on. Look what happens if we were to add 1 squared plus 1 squared. We get 2. Not very profound. If we take 1 squared plus 2 squared, we get 5. Well, now that's interesting. If we take 2 squared plus 3 squared, 4 plus 9, we get 13, which is a Fibonacci number. If we take 3 squared plus 5 squared, 9 plus 25, we get 34, which is a Fibonacci number. In fact, it looks like the sum of the squares of Fibonacci numbers is always a Fibonacci number. That is to say, Fn squared plus Fn plus 1 squared is F2n plus 1. Here's another pattern. What would happen if you added up the sums of squares, not of 2 consecutive Fibonacci numbers, but all the Fibonacci numbers? What would you get? Infinity, right? Because they go on forever. Okay, better question. What if you were to add up all those numbers and then stop at some point? Okay, so we have 1 squared plus 1 squared is 2. And 1 squared plus 1 squared plus 2 squared is 6. And 1 squared plus 1 squared plus 2 squared plus 3 squared is 15. And the sum of the squares of the first 5 Fibonacci numbers is 40. The sum of the squares of the first 6 Fibonacci numbers is 104. Okay, so let's look at those numbers. 2, 6, 15, 40, 104. They're not Fibonacci numbers. But if you look closely, I claim the Fibonacci numbers are buried inside of them. Do you see them? Look, 2 is 1 times 2. 6 is 2 times 3. 15 is 3 times 5. 40 is 5 times 8. 104 is 8 times 13. 2, 3, 5, 8. Who do you appreciate? Fibonacci, of course, right? So there they are, 1 times 2, 2 times 3, F2 times F3, F3 times F4, F4 times F5. In fact, in general, if you were to take the sum of the squares of the first n Fibonacci numbers, you get the nth Fibonacci number times the n plus first Fibonacci number. I won't prove this for you, I'll just revel in its beauty. Here's another beautiful pattern. Suppose we were to take, let's fix our attention on one of the Fibonacci numbers, like let's say F4 here, okay? And if we were to multiply its neighbors, say F3 and F5, then we see that 2 times 5 is 10, which was 1 away from 9, that is 3 squared. If we were to circle, say, the number F5, which is 5, and multiply its neighbors, we get 3 times 8, which is 24, which is 1 away from 25. If we were to take 8 squared, multiply its neighbors, 5 and 13, we get 65, which is 1 away from 8 squared, 64. Do you see the pattern? It works even with the lower numbers, with F1 times F3 is 1 away from 1 squared, and F2 times F4 is 1 away from F3 squared. In general, the pattern seems to be that if you take the n minus first Fibonacci number times the n plus first Fibonacci number, you get the square of the nth Fibonacci number plus or minus 1. Always 1. In fact, we can say it more precisely that fn minus 1 times fn plus 1 minus fn squared is equal to minus 1 to the nth power. What if we took the neighbors, instead of making them 1 apart, we made them 2 apart? Okay, so we'll focus here on F3. And if I take its neighbors 2 to the left and 2 to the right, I have 1 times 5, which equals 5, which is 1 away from 4, 2 squared. Let's do another example. If I were to take the number 3 and look 2 to its left, 2 to its right, I have 1 times 8, which is 8, which is 1 away from 9, from 3 squared. If I were to take the number 5 and look 2 to its left, 2 to its right, I have 2 times 13 is 26, which is 1 away from 25. You see the pattern? Here, again, we look at the number 8, 2 to its left, 2 to its right. 3 times 21 is 63. That's 1 away from 64. And so the general pattern is that fn minus 2 times fn plus 2 is 1 away from fn squared. It's either 1 higher or 1 lower. In other words, fn minus 2 times fn plus 2 minus fn squared is minus 1 to the n. What if you were to look 3 away, or 4 away, or 5 away? Well, if you look 3 away, we see the same sort of pattern. Let's just take, let's circle the 5th element this time, right? If we were to go 3 away, that would put us at 1, and 3 away here would put us at 21. This time it looks like we're 4 away from 25. If we were to take this number here, 8, and we were to go 3 away, that's 2, and 3 away, that's 34. Multiply those two together, we get 68, which is, again, 4 away from 64. In fact, the difference between them is either going to be 1, 1, 4, 9, 25, 64. We get the squares of the Fibonacci numbers as their difference. Let's go from looking at multiplication properties to some division properties, okay? Let's look at the ratios of consecutive Fibonacci numbers. For instance, 1 over 1 is 1, no problem. 2 over 1 is 2. 3 over 2 is 1.5. 5 over 3 is 1.666. 8 over 5 is 1.6 exactly. 13 over 8 is 1.625 exactly. And then, look what's happening. 21 over 13 is 1.615, ... There's some more stuff at the end of that. And so on. The next ratio, 1.619, 1.617, 1.618, 1.617. These ratios seem to be getting closer and closer together. As a matter of fact, if you were to take those ratios and go farther and farther and farther out in the Fibonacci sequence, then what those numbers are getting closer and closer to is 1.618033989, etc., which is 1 plus the square root of 5 over 2. This is known as the golden ratio. It's been said that the golden ratio has all kinds of magical and mystical properties. It certainly has some beautiful mathematical properties. Let me say a few words about those. For instance, if you were to take a rectangle with dimensions 1 and 1.618, and what I really mean is 1 plus the square root of 5 over 2, but we'll abbreviate that by calling it 1.618. If you were to take that rectangle and cut out from it a square, a 1 by 1 square, then what you're left with is a rectangle with height of 1 and of length 0.618. Take that rectangle, now let's turn it 90 degrees. So now it has height 0.618 and a length of 1. And what you have is a rectangle that's completely proportional, completely similar to the first rectangle. Okay, so that the ratio of 1.618 over 1 is exactly the same as the ratio of 1 over 0.618. It's been said that this rectangle is considered to be the most beautiful rectangle because it has these properties. I think, however, when the experiments have been done, when they've actually taken this to psychology classes, you know, they find that the prettiest rectangle is somewhere in the neighborhood of 1.6, 1.618, but it might be as low as 1.57 or 1.65. There's, I think, a little too much temptation to ascribe any number that's even remotely close to 1.618 and calling it the golden ratio. It's been said, for instance, that the human body, in the book The Da Vinci Code, they said that the human body was a testament to this number, 1.618, phi. And they'd say that if you measured yourself from head to toe, and you measured yourself from belly button to toe, that the ratio was always 1.618. Now, I haven't personally done this experiment, but I've heard others have, and the answer is, unfortunately, no. So there's an awful lot of myth. Yes, Fibonacci numbers do show up in nature, but not as often in fine arts and physiology as has been claimed, at least in my opinion. Well, here's another connection between the golden ratio and the Fibonacci numbers. There's an exact formula for the nth Fibonacci number. It's a beautiful formula, actually. It says that the nth Fibonacci number is 1 over root 5 times 1 plus root 5 over 2 to the nth power minus 1 minus root 5 over 2 to the nth power. This is called Benet's formula. I'm amazed that that formula produces whole numbers, much less produces the Fibonacci numbers. But in fact, the nth Fibonacci number is exactly what comes out of that formula. And that formula can be used to explain many of the Fibonacci numbers' beautiful properties. So as I've said, the Fibonacci numbers appear in nature. If you study pineapples, sunflowers, they actually show up there. In computer science, in arts, in crafts, even in poetry. Poetry, I hear you cry. Let me show you a piece of poetry. If you've ever recited a limerick, right? How does a limerick meter go? It says, dee-dum, dee-dee-dum, dee-dee-dum, dee-dum, dee-dee-dum, dee-dee-dum, dee-dum, dee-dee-dum, dee-dum, dee-dee-dum, dee-dum, dee-dee-dum, dee-dee-dum. I know, it's a dumb limerick. But if you count the D's and the dums in each line, look at what you get. If we count each line, look what we have. The total number of D's and dums in the first line is 8 syllables, 8 syllables, 5 syllables, 5 syllables, and 8 syllables. How many D's in the first line? 5. How many dums? 3. So we have 5 and 3, 5 and 3, 3 and 2, 3 and 2, 5 and 3. We're full of Fibonacci numbers. In fact, the total number of syllables in the limerick is 34, a Fibonacci number. Number of Ds is 21, a Fibonacci number. The number of Dums is 13, a Fibonacci number. I was so inspired by this fact that I composed myself my own Fibonacci limerick, which I will end on this note. I think Fibonacci is fun. We start with a 1 and a 1. Then 2, 3, 5, 8, but don't stop there, mate. The fun has just barely begun.